Section 6.3, Trigonometric Equations. So first off, as a reminder, we're working with this unit circle to keep everything straight, and we have to be concerned about the range of our inverse trig functions. And as a reminder, here are the ranges. Now, what we're about to do, though, is we're about to be concerning ourselves with solving equations of trigonometric functions, and so the inverse functions are going to come into play, but they're not the whole story, they're just a piece of it. And so let's just start with a general idea. Let's say we have the equation sine of theta is equal to a half. We want to determine whether the following values for theta are solutions of that equation. Well, what can we do? Well, if you're given values, there's nothing wrong with just taking those values and plugging them in and seeing if you get the correct answer. So we can do exactly that. Well, let's evaluate sine of pi fourths. But sine of pi fourths is root 2 over 2. That's not a half, which means that pi fourths is not a solution. Well then, I've got sine of pi sixth. Sine of pi sixth is 1/2, and that's exactly what we need, and so that works out. Then let's try sine of negative pi sixth. But sine of negative pi sixth, that's going to be negative 1/2, but that's not going to work, so that's out. Then let's consider sine of negative 7 pi sixth. Sine of negative 7 pi sixth. Well, if you want, remember that you're doing clockwise rotations, and so 7 pi sixth actually lives right here, which equates to a coterminal angle of 5 pi sixths. And the sine of 5 pi sixths is 1/2, and so that works out. Now what's important to note here is that if we were trying to find the solutions for this sine of theta, remember that the problem is that our trig functions are periodic. Thus, there can't exist an infinite number of solutions for any trigonometric equation. And so we have to be careful about this, and we may have to write somehow an infinite number of solutions, but we have to give a proper formula for that infinite number of solutions. On the other hand, sometimes we're just going to limit where we find our solutions from, and so we're going to restrict ourselves on some smaller interval, find the smaller number of solutions, and give that answer as well. So we may have to do both, but let's think about this infinite number of solutions. So we want to give a general formula for all the solutions of the equation sine of theta is equal to 1/2. Well, let's think about this on the unit circle real quick. On the unit circle, we know that at pi sixth and all of its coterminal angles, we know that sine of pi sixth is equal to 1/2. We also technically know that sine of pi sixth plus any coterminal angle, so 2 pi times any k, where k is an integer, that's always going to give us a half. And so technically I claim that this is going to be the formula for this smaller angle. Well, of course it's useful to then remember that all students take classes. And so sine being positive in the first and second quadrant, there's this other side over here that has a reference angle of pi sixth. But we found that value, remember, to be specifically the angle rotation of 5 pi sixths. And so 5 pi sixths is also going to be solution. So sine of 5 pi sixths is a half. But if we were trying to generalize that, you could say that as sine of 5 pi sixths and any of its coterminal angles, which is plus 2 pi times k, where k is an integer, and know that we will get 1/2. And so that's actually going to be the other formula general formula for our solutions of the equation. Now, watch out, because my labs is going to specifically say things like that first angle you use needs to be between 0 and 2 pi. So you need to give the answer between 0 and 2 pi plus 2k pi, and they're going to base it off of some smaller angle and then the larger angle that we found. So just watch out for the phrasing in my labs. Alright, let's extend this concept. So we did it for sine, now let's do it for cosine. So we want to know, where is cosine of theta equal to 1/2? Well, if you were to look at the unit circle and find everywhere that the x value is 1/2, all of those angles would be the smallest set of angles that would give us the solution cosine of theta is equal to 1/2. And so if I look at the unit circle, I notice that x is 1/2 here at pi thirds, and so I know that cosine of pi thirds is equal to 1/2, which, if we get pi thirds, then we need to deal with every coterminal angle, which means that cosine of pi thirds plus 2 pi k, where k is an integer, will also equal 1/2. So any coterminal angle of pi thirds will give us that solution. Well, what else happens? Well, remember that all students take classes, and so cosine being positive in the first quadrant and in the fourth quadrant means that we're also going to have to deal with the reference angle of pi thirds in the fourth quadrant, and recognize that that is a coterminal angle with something between 0 and 2 pi being 5 pi thirds. And so I know that cosine of 5 pi thirds is also going to equal 1/2. But since we do need a general formula, that is, we need all of the possible coterminal angles of 5 pi thirds, how could we write that? Well, that's going to be cosine of 5 pi thirds plus 2 pi k, where of course k is an integer. Well, those will also equal 1/2. And so notice that these are my two general formulas, and so let's type them out. There we are. If we let k be an integer, then based on the smaller angle theta, pi thirds plus 2k pi, or 2 pi k, is going to be that first set of infinite solutions, and then based on the larger angle, theta is going to be 5 pi thirds plus 2k pi. So in general, when we're solving trigonometric equations, what should we do? Well, to solve them, first isolate the trig function, or functions, depending upon what we have going on. We're going to see that there's going to be some interesting situations occurring. You may have to factor, so all of the stuff that we learned in pre-cal and algebra, still in play. You may also have to use an identity, so any of the identities that we've already learned or that we will learn may come into play in solving these trig equations. Then, once you've isolated that trig function, you can use its inverse to free the variable. Now, I didn't do that in the previous steps just because we could look at the unit circle, but from here on out I am going to use the inverse to help isolate our values. Then you need to find all the answers, or if it gives you a restriction, just find them in that solution set that they've asked for. And so, in general, if we're working in radians, which the majority of our class here is working in radians, you've got to add 2 pi k, usually. Or, if you're working in degrees, k times 360 degrees. Alright, so now we have 2 cosine theta minus root 3 is equal to 0. So let's actually find all of these solutions as asked. So first, they want us to solve the equation for theta being between 0 and 2 pi. So really, we're just working off of the unit circle after we do the algebra. So how do we do this? Step 1, isolate the trig function. So if cosine of theta is my trig function, I need to get it by itself. So let's do algebra. How about we add root 3? Add root 3. That's then going to be 2 cosine of theta is equal to positive root 3. Then we can divide by 2. Then we can divide by 2. I then get that cosine of theta is equal to root 3 over 2. Then I say free the variable. So that means cosine of theta is equal to root 3 over 2 means take cosine inverse of both sides. And then cosine inverse of cosine is going to give a theta. And then cosine inverse of root 3 over 2 is what we're about to find. But then cosine inverse of root 3 over 2, if you consider your unit circle, the x value is root 3 over 2 at pi sixth. So that's going to be the smallest one angle off of the range values of the cosine inverse. But let's draw our, at least think about our unit circle, where we recall that all students take classes, that is, where are things positive or which trig functions come out positive in which quadrants. And since pi 6, well, pi 6 occurs here in the first quadrant, we know that that is the first place that cosine is going to be positive. But like I said, that range restriction that occurs on cosine inverse says we're only going to get solutions between 0 and pi. So I need to deal with also how pi 6 occurs in the fourth quadrant, which really is the reference angle of pi 6. But the reference angle of pi 6, if we're trying to find a value between 0 and 2 pi, that angle is then going to be what? Well, it's going to be 2 pi minus pi sixth, or 11 pi sixth. And so, for the angle of 11 pi sixth, we found another solution between 0 and 2 pi that forces cosine of theta to be equal to root 3 over 2. And so, when I'm solving the equation for theta, when 0 is less than or equal to theta is less than 2 pi, that is, theta needs to be the values between 0 and 2 pi, including 0, excluding 2 pi, our solutions are theta is equal to pi sixth, and theta is equal to 11 pi sixth. So that's our first set of solutions. But then, we need to give a general formula for all of the solutions. Well, remember that each one of these angles have an infinite number of coterminal angles, and we need to write exactly that. So, let k be an integer. Then, theta has two solution sets. That's going to be pi sixth and all of its coterminal angles, 2 pi k. And then, theta is also going to equal the other angle, 11 pi sixths, plus all of its coterminal angles, 2 pi k. So now what we want to do is we want to list the first 5 solutions greater than or equal to 0. And so really you're thinking about starting your rotations on the unit circle and seeing which ones you come to, and then just keep making circles on the unit circle until you've covered all of those possible first 5 rotational angles. So really we can just calculate using our formulas for theta if we so desire. But I'm going to make my life easy. If I let k equal 0, well, then pi 6 plus 2 pi times 0 is pi 6 plus 0, or pi sixth. Then we go to the next one, 11 pi 6 plus 2 pi times 0, that's going to be 11 pi 6. Then I go back up to the next one here, and I let k equal 1. So when k equals 1, I get pi 6 plus 2 pi. I can then find common denominators. Well, 6 times 2 is 12. 12 plus 1 is 13 pi sixth. And so the next one that occurs is 13 pi sixth. Then letting k equal 1 for the next one. And for the reference here, these were k equals 0. So then if I do 11 pi sixth plus, let k equal 1, that's going to be plus 2 pi. But then multiply by 1 in disguise, that's 6 over 6. Well, that's going to give me 12 pi plus 11 pi, or 23 pi 6. Then we can go back to our first equation and let k equal 2, in which case we get pi 6 plus 2 pi times 2. That's really 2 full rotations past pi 6, so that's going to be 4 pi plus pi 6, or multiply by 1 in disguise, 6 over 6. That's 24 plus 1, or 25 pi 6. And so that's the first 5 solutions greater than or equal to 0, and we just use k into our formula for all the solutions to get it. If you would rather just consider the unit circle and count your pi 6, getting every situation in the first and fourth quadrant after you rotate past 0 in the positive counterclockwise direction, you're good to go. Alright, so let's solve this one. Let's say we want to solve the equation sine of 3 theta is equal to negative 1, when first we need to find the thetas between 0 and 2 pi. Then we're going to simplify and give a general formula for all the solutions. Now, a couple things to note. Remember that this 3 here is a period adjustment. And this is going to come into play because when we're trying to find all of the solutions between 0 and 2 pi, we have a little bit of work to do. Okay? So, that period adjustment, remember that's going to allow for the fact that 2 pi divided by b, or 2 pi divided by the absolute value of 3, is going to be 2 pi thirds. And so really, once I find the smallest, or all of the smallest angles that are possible as solutions for sine of 3 theta is equal to negative 1, then I can just add 2 pi thirds to those values, and I can get all of my solutions. So let's do this. First off, note that sine of 3 theta is equal to negative 1 is already isolated for the trig function. So if I've got sine of 3 theta is equal to negative 1, then of course we need to deal with the fact that I can take the sine inverse of both sides, and then I get that 3 theta is equal to sine inverse of negative 1. Well then, of course, because of our range restrictions on sine inverse of negative 1 is actually going to give us negative pi halves. Well then, of course, we just continue with algebra. Divide by 3. Divide by 3, we then get that theta is equal to negative pi halves times 1 over 3, or that is negative pi sixth. Alright. Good news, bad news. The good news is that we can think about the fact that this is then going to be, where does negative pi sixth live? Negative pi sixth on the unit circle lives right here, right? Alright. But the problem is that for our first set of solutions, we've got to find the solutions between 0 and 2 pi. Negative pi sixth is not there. So what I really need to do is I need to consider what is that angle on the unit circle, but with a positive orientation angle between 0 and 2 pi. Well, that's 2 pi minus pi sixth, which ends up giving us 11 pi sixth, right? So negative pi sixth isn't the one we want 11 pi sixth. So that's going to be one of our solutions between 0 and 2 pi. Alright, but then we have to think about some other stuff. This is actually going to be theta, we now know, is going to equal 11 pi sixth. That is one of my solutions. But there's a problem. Now at this point, I claim we have to be careful, because a couple of things are going to happen. Or really, there are two good approaches depending upon which way you want to go. 11 pi sixth is definitely one of the solutions to this problem. Now, 11 pi sixth is really close to 2 pi, so we can play with the period of this function, and I claim if you want, we can find all the rest of our solutions. So this is one approach. So first off, 11 pi sixth is one of my solutions. If you plug it in here, sine of 3 times 11 pi sixth, you will recognize that you will get negative 1. Great, wonderful, good. But we need to deal with all of the other locations where sine of 3 theta are going to give us negative 1 for all our other thetas. How can you find that? Well, if we can recall that all of our trig functions being periodic, sine of 3 theta equaling negative 1 is really the idea that sine of 3 theta, which I claim is just a sine function with a period adjustment, looks like this. Now the question is how many times does the new period force this function to occur between 0 and 2 pi? Well, since our period is 2 pi thirds, I'll actually go ahead and let you know what's going to happen is that it really ends up being 3 times. And so the locations where this ends up being negative 1 are here, here, and here. I claim that this one over here actually ends up being 11 pi sixth. Now, what does that mean I can do? Well, that means that I can take this value here and I can add or subtract the period to get all the values between 0 and 2 pi. And that's exactly what we want to do. So if I've got 11 pi sixth, let's do a quick bit of arithmetic. 11 pi sixth, and I'll let you check this, but if you take 11 pi sixth and you add 2 pi thirds, that being the period adjustment that we have for this function, well, you're actually going to get a value bigger than 2 pi, and so that's not working for us. So now what I want to do is I want to subtract 2 pi thirds and iterations of 2 pi thirds until I get all of my solutions. So I'm going to subtract 2 pi thirds. And if I subtract 2 pi thirds, I need a common denominator. So multiply by my 1 in the skies, that's 2 over 2 here. 2 times 3 is 6. 11 pi minus 4 pi sixth is 7 pi sixth. So I claim that one of my other solutions now is 7 pi sixth because 7 pi sixth is between 0 and 2 pi. If you plug it back into sine of 3 theta, sine of 3 times 7 pi sixth, you will confirm that that is exactly one of our other solutions. Well then, what else can we do? Well, let's subtract the period again from this 7 pi sixth. So 7 pi sixth minus that period 2 pi thirds. Multiply by my 1 in disguise, that's going to be 4 pi over 6, so 7 pi minus 4 pi. That's going to be 3 pi sixths, but that's going to equal pi halves. Then we can confirm that pi halves is between 0 and 2 pi, that's good. And then plug in pi halves. 3 times pi halves is 3 pi halves, but recognize that sine of 3 pi halves is negative 1. So that's another one of our solutions, pi halves. Well, I claim that this is all of the solutions between 0 and 2 pi. Well, let's confirm that if you really want. Well, what's pi halves minus that period 2 pi thirds? Pi halves minus 2 pi thirds, well, that's going to give me what? Multiply by 1's in disguise to get common denominators. That's going to be 3 over 3 on this side and 2 over 2 on this side. But then 3 pi minus 6 pi, that's going to be a negative value, and since it's negative, it's less than 0, so we're not going to care about it. Well, then, recognize that at this point, if I want to give a general formula for all solutions, the truth is what we did right here is actually exactly that formula. You take your smallest angle value that we found here and add every period to that, and that will give you all your solutions. And so our general solution for all thetas is going to be theta is equal to, and given of course that k is an integer, theta is then going to be equal to pi halves plus the period that we found, 2 pi thirds times integer multiples. So 2 pi k over 3. And so this is actually all of my solutions. Alright, so now let's use a calculator to solve the following equations on the interval between 0 and 2 pi. So, if I have sine of theta is equal to 0.4, what happens? Well, first off, all you have to do is take sine inverse of both sides, because notice that the trig function is already isolated. And so that theta is then going to be equal to sine inverse of 0.4. If you're looking at your unit circle, you'll recognize that 0.4 is not there, which is exactly why they said use a calculator. I get that theta is now approximately equal to 0.4115 or 41, rounding to 2 decimal places. But be careful. Although sine inverse only has one solution, that is 0.41, the equation sine of theta equal to 0.4 will actually have at least 2 solutions between 0 and 2 pi. And so remember that all students take classes. Note that this is positive, which means that we're going to be in the first quadrant. So the first quadrant has a rotation angle of 0.41. But we're also going to have to deal with the other places where sine is positive. So that's going to be in the second quadrant with the reference angle of 0.41. And so then my second angle is really going to be this right here, which is really going to be pi minus 0.41. And so I claim that my other angle is going to be approximately 2.73. And these are going to be our 2 rounded solutions for that trig equation. Let's try it again. Here we have secant of theta is equal to negative 1.5. So let's take secant inverse of both sides. So that tells me that theta is going to be equal to secant inverse of negative 1.5. But of course recall that if we're trying to evaluate this approximately, then of course the secant function is the same thing as the reciprocal of the cosine function, or in terms of its inverse is going to be cosine inverse of 1 divided by negative 1.5. And so I can then get that theta is approximately 2.30. And so we do get one solution, but recall that of course our inverse trigonometric functions are only going to give us one answer. We have to extrapolate to the fact that our equations can have more than one solution, and so all students take classes, noticing that secant is negative. Remember that secant of theta is the same thing as 1 over cosine of theta. Thus, cosine being negative means that this 2.3, if you can recall, is actually going to be over here. This is 2.3. Now, how did I get that that's 2.3 in terms of radians? I recognize that, of course, pi radians is over here at the negative x-axis, and 2.3 is less than pi, so I know I'm in the second quadrant. But then we need to find the other angle that's going to exist in the third quadrant, right? So it's going to exist down here in the third quadrant because that's where cosine is also going to be negative. So I need to figure out what that angle is going to be. Well, how can I do that? Well, I can find the reference angle. Well, the reference angle here is going to be what? Well, that's going to be pi minus 2.3. But pi minus 2.3 is going to give me 0.84. Well, then I can use that reference angle of 0.84, reference angle here. So I add 0.84 to pi. So my other solution is going to be pi plus 0.84, which I get to be 3.98. And so those are going to be our two solutions, rounded to two decimal places, for the equation secant of theta is equal to negative 1.5. Then we want to solve this equation for sine squared theta is equal to 1, and specifically we were just going to limit ourselves to between 0 and 2 pi. We're not going to concern ourselves with all of the solutions, just the between 0 and 2 pi solutions, just like we did a moment ago. So step 1, isolate our trig function. So if I have 4 sine squared of theta is equal to 1, step 1, isolate the trig function, divide by 4, divide by 4. Then we get that sine squared of theta is equal to a fourth. At this point, we have sine squared of theta. We have sine squared of theta is equal to a fourth. Well, how do you undo square? You take the square root. But be careful. Remember that when you take the square root of a square, you have to be concerned about two things. You've got to be concerned about all the positive solutions and all the negative solutions because, of course, squares undo negatives, right? And so really this tells me that sine of theta is going to equal positive root 1 over 4 and negative root 1 over 4. And so I'm going to really write this as two equations. Sine of theta is then going to be equal to square root of 1 is 1 over square root of 4 is 2. So sine of theta is equal to 1/2, and sine of theta is equal to negative 1/2. Okay, two equations now. If you like that plus minus notation, that's okay, but please be aware that, of course, it does create these two problems. Sine of theta is equal to the positive 1/2, and sine of theta is equal to the negative 1/2. Great. Then, sine inverse of both sides. I get that theta is going to be equal to sine inverse of a half, which, if you consider a unit circle, where is that going to give us the solutions for sine inverse? Specifically, that is at pi 6, right? So that's our sine inverse solution. We'll come back to that in a moment. But then, take sine inverse of both sides for this one. Thus, we have theta is equal to sine inverse of negative 1/2. But sine inverse of negative 1/2, based on our range values for sine inverse, that's specifically going to be negative pi 6. Okay, so we got a little bit of work to do because, of course, we want our solutions between 0 and 2 pi, and negative pi 6 isn't there, and we might not be done yet anyway. So, a couple things. First off, theta equals pi 6. But remember that because of the range restrictions, sine inverse is only going to give one solution, so I have to deal with the other places where I would get a positive 1/2 for the sine function. So all students take classes. I know that my first solution is at pi 6. That's positive, right? Okay, great. That's going to be one of my solutions. I'll go ahead and write that down, pi 6. But where else is sine positive? Well, sine is also going to be positive to get this positive 1/2 in the second quadrant. So then I know I've got to deal with this reference angle of pi 6. And so to find that angle, specifically you can take pi, because of course pi is the negative x-axis, minus pi 6. And pi minus pi 6 is going to give us 5 pi 6. And so I claim our second solution from this equation over here is 5 pi 6. Great. Well, then I've got to come back over here to this theta, this negative pi 6. All right, well, negative pi 6 is down here, right? Okay, but negative pi 6 is not between 0 and 2 pi. Since it's not between 0 and 2 pi, we need to find the reference angle that's between 0 and 2 pi that equates to negative pi 6. I'm sorry. We have to find the coterminal angle that gives us negative pi 6 that's between 0 and 2 pi? Well, specifically that's going to be 2 pi minus pi 6, or 11 pi 6. So my next solution set is actually going to be 11 pi 6. Great. But we also have to watch out, because not only is sine negative in the fourth quadrant, sine is also negative in the third quadrant. And so then you have to be concerned about this one, where this is a reference angle of pi 6. And so if that reference angle of pi 6, that's going to be pi plus pi 6. But pi plus pi 6 is actually 7 pi 6. And so now I know that my other solution is 7 pi 6. Well, 4 times sine squared of theta being equal to 1, that's true for all of these thetas. So you do have to be careful. Now, it's of course true that we could deal with this generalized solution, but we weren't asked to, so I'm just going to restrict my solutions between the solutions to be the solutions between 0 and 2 pi. Continuing, let's solve the following equations on the interval between 0 and 2 pi. So if I have sine squared of theta minus sine of theta is equal to 0, well, everything's already in terms of a single trig function. That's a sine theta function. In general, I'm going to say that you should always have a single trig function. If you can, you're going to use some identities to get to a single trig function. But at this point, there's nothing that I can do to combine any like terms. Sine of theta and sine squared of theta are not like terms, therefore they cannot be combined. So we've got to play an algebra trick. We're going to factor. So notice that sine squared of theta and sine of theta has a greatest common factor of sine of theta. So factor out sine of theta. Alright, sine squared of theta divided by sine of theta, that's going to leave me with sine of theta. And then negative sine of theta divided by sine of theta is going to leave me with negative 1. That's equal to 0. At this point, we can use the zero product property. Sine of theta is equal to 0, and sine of theta minus 1 is equal to 0. Zero product property. Well, then let's just figure out our solutions. We can take sine inverse of both sides here. Sine inverse of sine of theta, sine inverse of 0. Well, sine inverse of sine of theta leaves me with theta. That's now equal to sine inverse of 0. And so sine inverse of 0, using our unit circle, that's going to occur specifically in one location for the restriction on range for the sine inverse function. That occurs at 0 radians. But be careful, because we have to be concerned about everywhere that sine is 0. And so everywhere that sine is 0, that's going to be when the angle is 0 and when the angle is pi. And so now I know that theta has to be 0 and it has to be pi. If nothing else, look at the unit circle and remember you're looking for the y values to be 0, because that's where sine of theta is equal to 0, and that occurs at 0 and pi. Okay, so we got all the solutions for that section. Then, this one I need to finish solving, so add 1, sine of theta is equal to positive 1. Take sine inverse. So that's going to be theta is equal to sine inverse of 1. But sine inverse of 1, that only occurs at pi halves based on our range restrictions for sine. And then let's confirm that that's the only location where we get sine of theta equaling positive 1. But if you look at your unit circle and you consider where all the y values are 1, that's only going to occur in one place, and that's at the pi halves situation. And so pi halves is our only other solution. And we're done. Now notice we have 2 cosine squared of theta minus cosine of theta minus 1 is equal to 0. Once again, my statement previously, do we have a single trig function to work with? Yeah, it's just cosine. So anytime you see this, I claim that this is really a quadratic function. Now, I have a trick for you if you're struggling with recognizing that it's a quadratic function. The trick here is that if you so desire, you could do what's called a substitution. You could say, hey, the cosine theta is messing me up, so I'm going to pretend that cosine of theta is equal to y. Alright, if we do that, then what is this going to be? This is going to be 2 y squared minus y minus 1 is equal to 0. Now, in the long run, this isn't always going to be the best approach, but especially when you're trying to get used to doing algebra with trig functions, maybe it's useful to do the substitution. But be careful, because if you solve this quadratic formula, if you solve this quadratic equation, 2y squared minus y minus 1 is equal to 0, you'll solve for y. not for cosine of theta. And so you'll have to resubstitute and finish the equation. But the goal is that in the long run, you are able to factor this just from the cosine function. And so, real quick, just as an algebra reminder, how can I factor this? Well, you can use the AC method. That's my personal preference. A is 2, C is negative 1. 2 times negative 1 is negative 2. Then we can look for two numbers that multiply to give me negative 1, but sum to be negative 1, which is my inner term here. And so the sum equaling negative 1 is really going to be negative 2 plus 1. And so I'm going to rewrite that middle term, 2y squared minus 2y plus 1y minus 1 is equal to 0. Then you can factor by grouping. And so then notice the GCF over here is 2y times y minus 1 plus, well, what's factoring out here? That's just going to be a positive 1 times y minus 1. Then this factors completely to be 2y plus 1 times y minus 1 is equal to 0. Then we can use the zero product property, and we can finish and we can solve for y. But I want to work with the trig function because you're going to get the exact same thing in the end when you resubstitute, but I just wanted to remind us of the factoring techniques. And so I'm going to play all these same games. Notice that negative 1 times 2, I'm going to factor this. This is then 2 cosine squared of theta minus 2 cosine theta plus cosine theta minus 1 is equal to 0. So we force the factor by grouping. I recognize that the GCF on the left is 2 cosine theta times cosine theta minus 1 plus, well, the factoring here, we can only factor out a 1 times cosine theta minus 1. Then factor out this binomial, cosine of theta minus 1. That's then going to give me cosine of theta minus 1 times 2 cosine of theta plus 1 is equal to 0. Then we can use the zero product property. That's going to be cosine of theta minus 1 is equal to 0, or 2 cosine of theta plus 1 is equal to 0. So add 1, cosine of theta is equal to 1. For what angles? Then we can, of course, take cosine inverse of both sides. That's then going to give me that theta is equal to cosine inverse of positive 1. Well, cosine inverse of positive 1, that's going to equal 0. But then we do have to be careful, so we need to check our unit circle. Is there anywhere else where cosine is going to equal 1, or where, of course, the x value is 1? But notice that that's the only location. So I claim that our first solution of theta is 0. Then we need to move over to 2 cosine theta plus 1. So how about minus 1 minus 1? So 2 cosine of theta is equal to negative 1. Divide by 2, divide by 2. Cosine of theta is equal to negative a half. Then we can use cosine inverse. Cosine inverse of cosine theta, cosine inverse of negative 1/2. That's going to give me theta is equal to cosine inverse of negative 1/2. But cosine inverse of negative 1/2, remember your range restrictions for cosine inverse. That puts us in the second quadrant. And so the x value is negative 1/2 at 2 pi thirds. But that's only one of our solutions. So then I have to remember that all students take classes. Cosine, this is negative, right? So cosine is negative where? It's going to be negative in the second quadrant. So 2 pi thirds, we just found that one. And it's also going to be negative in the third quadrant. So I need to find that reference angle. But the reference angle here will equate to the reference angle here. That's just going to be pi minus 2 pi thirds. Pi minus 2 pi thirds is going to leave me with pi thirds. And so my reference angle is pi thirds here, and it's also pi thirds here. So then to find my other solution, I take pi, because of course pi is my negative x-axis, pi plus pi thirds to get my other solution, and that's going to be 4 pi thirds. Now, of course, I want you to notice that I am taking some extra steps, but if you were to look at your unit circle, a complete unit circle, and you recognize that the x value, -1/2, occurs in two locations on a unit circle, that's specifically at 2 pi thirds and 4 pi thirds, you would get those exact same solutions. Notice also that you can do the same thing with the zeros. I notice that I have a quadratic form, and I have signs, and so this is going to be a factoring problem. So again, I'm going to use the AC method. Leading coefficient 4 times 5. 4 times 5 is 20. Therefore, I'm looking for two numbers that multiply to give me 20, positive, and then sum to equal -9. And that sum is going to be -4 minus 5. Recognize that -4 times -5 gives us positive 20. And so we're perfectly fine there. Then rewrite our middle term. That's going to be 4 sine squared theta minus 5 sine theta minus 4 sine theta plus 5 is equal to 0. We've now forced the factor by grouping. Trap that negative in, but then of course that becomes plus. Notice that on the left the GCF is now sine of theta. Sine of theta times what's left over is 4 sine theta minus 5. Then I need 4 sine theta minus 5 to be in the next binomial, so I'm going to factor out a -1 times 4 sine theta minus 5 is equal to 0. Factor out that common binomial. That's going to be 4 sine theta minus 5 times sine theta minus 1 is equal to 0. Zero product property. 4 sine theta minus 5 is equal to 0. Sine theta minus 1 is equal to 0. Let's solve this one on the left first. Plus 5 plus 5. 4 sine theta is equal to positive 5. Divide by 4. Divide by 4. Sine theta is equal to 5/4. Now at this point I'm going to recognize something. I'm going to notice that sine of theta equals 5/4 is impossible. That is, the range of sine of theta goes between -1 and 1, and since I see that sine of theta being equal to 5/4 is actually not possible, this is going to give me no solutions. Then to the next one, sine of theta minus 1 is equal to 0, plus 1 plus 1. Sine of theta is equal to positive 1. Then I can take sine inverse of both sides. That is, theta is equal to sine inverse of positive 1. Then think about where will I find thetas such that I get sine inverse being 1. Well, specifically, via the range, that's going to be pi halves. And that's the only location where I'll get sine of theta being 1. Alright, I said that sometimes you may have to use trig identities. So this is one of those times. So notice that I've got cosine squared of theta is equal to sine squared of theta minus sine of theta. I said that earlier we really want to get everything in terms of a single trig function. So I see I've got sine squared of theta, and I've got sine of theta, and then I've got a cosine squared of theta. I think I really want to focus on this cosine squared of theta, and I want to see, is there any way I can write cosine squared of theta in terms of sine? Recall your identities. Well, there's one good, really awesome identity that occurs often enough, and that's the Pythagorean identity. Sine squared of theta plus cosine squared of theta equals 1. I recognize that I've got cosine squared of theta here, so let's isolate my Pythagorean identity for cosine squared of theta. So let's subtract sine squared of theta. Subtract sine squared of theta. I then get that cosine squared of theta is equal to 1 minus sine squared of theta. Okay, so then what are we going to do? Well, we're literally just going to replace cosine squared of theta with its equivalent, 1 minus sine squared of theta. Okay, so that's going to be 1 minus sine squared of theta is equal to sine squared of theta minus sine of theta. At this point, I recognize that I have some quadratic stuff, but I need to move everything to one side. So I'm going to add sine squared of theta, add sine squared of theta. I'm going to go ahead and subtract 1. Subtract 1, I'm then going to get that 0 is equal to 2 sine squared of theta minus sine of theta minus 1. I have a quadratic that I can now factor. And so if I use that AC method, I recognize 2 times negative 1 is equal to negative 2. Two numbers that multiply together to give me negative 2, but sum to equal negative 1, well, that's going to be negative 2 plus 1. And so that is going to be 0 is equal to 2 times sine squared of theta minus 2 sine of theta plus sine of theta minus 1. And so then I can force that factor by grouping. That's exactly what I've done here. So grouping. Find that the GCF on the left-hand side is 2 sine of theta. And so 2 sine of theta times sine of theta minus 1. And then over here, sine of theta minus 1, the only thing I can factor out is a 1. So that's going to be then sine of theta minus 1. And so then my greatest common factor is now that binomial. And so that's going to be 0 is equal to sine of theta minus 1 times 2 sine of theta plus 1. Then I can use the zero product property. 0 is equal to sine of theta minus 1, and 0 is equal to 2 sine of theta plus 1. So add 1, sine of theta is equal to 1. I can then take the sine inverse of both sides. I get then that theta, and I'm just going to do a rearrangement real quick, I'm just exchanging sides. Theta is equal to sine inverse of 1. But based on our range restrictions for sine inverse of 1 is going to be at pi halves. But if you confirm on your unit circle, there are no other locations for any other thetas, at least between 0 and 2 pi, in which you're going to get the output of 1, and so I claim that our first solution is pi halves, and that one doesn't give us another. Well then, let's work with this. 0 is equal to 2 sine of theta plus 1, so I'm going to subtract 1 from both sides, and I get minus 1 is equal to 2 sine of theta. Then divide by 2, divide by 2. I then get that negative 1/2 is equal to sine of theta. Then I can take the inverse sine function of both sides. I get that sine inverse of negative 1/2 is equal to theta. Sine inverse of negative 1/2, based on our range restrictions, is going to give me negative pi sixth. But if you would rather just use the unit circle and figure out for what theta measurements between 0 and 2 pi give us negative 1/2, that's an okay approach as well. But regardless, got to consider the whole thing. All students take calculus. We recognize that this is going to be in the fourth quadrant since it's negative, and since that's negative pi sixth, I recognize that this is actually the angle of 11 pi sixth, and so my next solution is 11 pi sixth. Then I have to be concerned about the fact that this also occurs in the fourth quadrant, and so in the fourth quadrant I had that reference angle of pi sixth. Really it was negative pi sixth, but reference angle of pi sixth added to pi plus pi sixth, that's going to give me 7 pi sixth, or if you had used your unit circle, you would have found all the places where the y value was equal to negative 1/2. Regardless, you would find also 7 pi sixth. And so I claim that our solutions between 0 and 2 pi are pi halves, 11 pi sixth, and 7 pi sixth. Let's do another one that requires an identity. So here we have secant squared of theta minus 2 tangent squared of theta is equal to 2/3. Now at this point, I'm just trying to think, is there an identity that relates tangent and secant? And I claim that there is, but if you forgot, if you can remember the first Pythagorean identity, sine squared of theta plus cosine squared of theta is equal to 1, you can derive the other one by finding, oh, well, sine squared of theta divided by cosine squared of theta will give me tangent, so I just need to divide everything else by cosine squared of theta. And so sine squared of theta divided by cosine squared of theta, that's going to give me tangent squared theta. Cosine squared of theta divided by cosine squared of theta, that's going to give me 1. 1 divided by cosine squared of theta, that's going to give me secant squared theta. And at this point, notice that I've actually found an equivalence of secant squared theta that's related to tangent. So I'm going to replace secant squared theta with its equivalent of tangent squared theta plus 1. So that's going to be tangent squared theta plus 1 minus 2 tangent squared theta is equal to 2/3. I'm just going to combine like terms first and see what happens. So I get tangent squared theta minus 2 tangent squared theta. That's going to be negative 1 tangent squared theta plus 1 is equal to 2/3. Yeah, it's quadratic, but since there's only one tangent here, I can move all the numbers to the right. How about minus 1 minus 1? I then get negative tangent squared of theta is equal to negative 1/3. Then I can divide by the negative, divide by negative 1. I then get that tangent squared of theta is equal to positive 1/3. Then we need to take the square root of both sides. But, of course, recall that when you take the square root of a square, you have to recall that it's going to be the positive and the negative solutions here. So that means that what we really have is tangent of theta is equal to the positive square root of 1 over 3, or 1 over root 3, which of course is the same thing as root 3 over 3. And we also have the fact that tangent of theta is equal to negative 1 over root 3, or root 3 over 3. Those are, of course, the same thing. Then I can take tan inverse of both sides. So then I get that theta is equal to tangent inverse of root 3 over 3. Then recalling that the range of tan inverse is between negative pi halves and pi halves, tan inverse of root 3 over 3 is going to be in the first quadrant, which ends up being pi sixth. Okay, so that's one of our solutions because that is between 0 and 2 pi, so theta is equal to pi sixth. Alright, but here we have to be concerned, but it's really easier for tangent because specifically remember that tangent has a period of pi, and because tangent has a period of pi, anytime I get one solution between 0 and 2 pi for a tangent function, I just add, because theta has an unchanged period here, add pi to pi sixth. And so if I add pi to pi sixth, well, in the third quadrant, because of course I'm still thinking about all students take classes, but in the first and the third quadrant tangent is positive, but the period really handles that for us. So pi sixth plus pi is going to give me 7 pi sixths. But then I have to worry about this other solution, so how about we take tan inverse of both sides here, so tan inverse of tan of theta, and then tangent inverse of negative root 3 over 3. So theta is equal to tangent inverse of negative root 3 over 3. Now for our range values, this one is a little problematic because this actually gives us the solution negative pi 6. Now of course this does not fall between 0 and 2 pi, and so if I were to think about that on our circle, negative pi 6 is here, but to make that be between 0 and 2 pi, I add 2 pi to that, and I'm going to get 11 pi sixths. 11 pi sixths. And so another solution is 11 pi sixths. But then we can also remember that because of the periodicity of tangent, I also get a distance of pi away from that. So if I subtracted pi from 11 pi sixths, 11 pi sixths minus pi, where we're going to specifically get 5 pi sixths. And so my last solution here is 5 pi sixths. And so these are all of the solutions between 0 and 2 pi.